Hello. So today, what hopefully we will be doing is deriving a time-independent form, or rather deriving a full form of of the Schrödinger equation in a cylindrical well. I always thought this was funny because I saw it in Young Sheldon, and he's there's an episode where he forgets the zeros of the Bessel function, and he's obviously learnt them off by heart because he's Young Sheldon. And it's all about how not everyone's perfect, blah blah blah. But then I sort of thought, well, wouldn't it be funny to actually have a go at deriving the Schrödinger equation in a cylindrical well? And so that's what we're going to be doing today. So we will begin by what we're going to do first is work out what the Schrödinger equation is. So we usually take it initially in a time-dependent form. And we start off with IH bar times this fraction, which is, my partials are going to have to be quite good today, and so are my phi's, because I can't really draw them very well, but we're going to do that. That's my phi of RT over dt is equal to the Hamiltonian of phi. Is that even a phi? No, that's a psi. Goodness me. Of psi. And in turn, that is equal to this minus h bar over 2 mu times the Laplacian plus v of rt, all times by that function again, the dreaded. And what we can do is, we know that the wave function rt can be factored into a time component. This is where it's going to get hard because this doesn't look like... Okay, right. Into a time component and a spatial component. And of course spatial in terms of the r, and then time in terms of t. So we're going to draw a little psi. It's going to look like that. And this of r is our spatial component, times big T of little t, which is our temporal component. And hence we know that IH bar times the partial derivative with respect to time of the wave function. The position of the wave function times the time of the wave function is equal to minus h bar over 2 mu times the Laplacian plus v of r, and now that thing from before, which we split above, of r and t of t, and that's our new split Schrödinger equation. We can further then say, because what we're attempting to do here is get a form of the equation that's time independent, we can say that IH bar times the spatial component times dt is equal to t, should be a t of t, times this big old thing, h bar over 2 mu Laplacian squared, and now our spatial component plus v r, that of r, put that in a square bracket, and if we divide the entire equation by our original wave function up here, which is that, we get that IH bar, or rather IH bar over t of t dt, lots of t's, is equal to that whole expression, which I understand I might be able to copy and paste. Let's see if... Oh, it's not happy. Oh no, it's happy. Am I still recording? No, we're okay. Good. I'm going to attempt to copy this whole thing and just paste it in again, because that may save some time. No, not that. There we go. Pop in 1 over, and then the temporal components, like that. Wonderful. So here we have so the left hand side of this depends on time, and the right hand side depends on position, and that's nice because now they're separate and we have a differential equation. So how are we going to solve the differential equation? If we set the right side equal to E, which is the total energy in the system, we know that both sides must equal that total energy, so we can say that IH over T dt dt is equal to E. Differential equation dt, that should just be a regular d, there's no partial, over t is equal to minus I times E over h bar dt, and integrate both sides, and we get that ln of t is equal to minus I E times t over h bar plus c. And so we know that if we do e to the power of both sides, we know therefore that t of t is proportional to e to the minus I times the energy times time divided by Planck's constant. Now the next thing we're going to do is similarly, however, we can equate the spatial side to E, and we simply get ourselves the time independent form of the Schrödinger equation. This will be useful shortly, hopefully. I haven't done that just pointlessly. Anyway, from what we had above, we can in fact say that this is kind of separate from that, so I'll pop a line there. Minus h bar squared over 2 mu times the Laplacian squared times that of r plus v of r again is equal to E. That. I could probably do that a bit neater. There you go. Now this is our time independent Schrödinger's equation, which is really useful. Now we have one more thing that we want to define here. Since we're working in a cylindrical well, we are working in cylindrical coordinates, and just to redefine if anyone's forgotten, here's our definitions for the relationship between Cartesian and cylindrical coordinates. So cylindrical coordinates work in terms of r and theta, kind of like polar but ever so slightly different. So we know that x equal to, r and phi, r cosine of phi, that should look more like a phi, there we go, and y is equal to r sine phi, and z is in fact z, since working in 3 dimensions, so that's useful because that stays the same. And now our r is of course the square root of x squared plus y squared, very similar to polar coordinates these, and phi is the arctan of y over x, not over z. There we go. That's our transformation. Now just to recap as to what the Laplacian is. It's been a while since you've done any vector calculus. We know that this is in fact the gradient function, the gradient operator, which is partial with respect to x, plus partial with respect to y, plus partial with respect to z. Oh no, don't do that. all squared, which is very simply the second partial derivative with respect to x, y, and z. Y squared plus partial. That's a very nice partial compared to my other ones that look more like cursed sixes. I'm happy. Now what I'd like to do is the first derivatives. So partial. We'll do it with respect to x first, and hopefully extrapolate for the others. What is this going to be? This is going to be partial r partial x times partial with respect to r plus the same but for phi. Partial phi. And if we calculate the partials of our corners here, we can in fact see, or maybe we can see if the computer decides to computer. There we go. We can in fact see if we take this first, so that would be partial r with respect to x, that's the partial derivative of x squared plus y squared, but to the half, which is half x squared plus y squared to the minus a half. This is in fact the chain rule. 2x, which simplifies to x over r, which is actually cos of phi. Cos of phi. Oh, sorry. From this identity up here, cos phi equals x over r. Simple. Now repeating for phi. Phi over partial x is equal to partial over the partial derivative of x arctan x over y, which you know is going to be horrible because it's an arctan, which is 1 over 1 plus y over x squared times minus y over x squared, which is minus y over x squared plus y squared, which is simply, that's r, what's minus y, it is in fact over r even, sorry, this is r squared, so we have minus y over r times 1 over r, which is just sine phi over r, minus sine phi over r, because of minus phi, minus sine phi over r, that is a phi, I hope so, it would be really sad if it wasn't. Phi, fee, fi, fo, fum. Is that how it goes? Yeah, sure. Anyway, so we can say that the partial with respect to x is cos phi times the partial with respect to r, and this is just from our identity above, and minus sine phi over r times the partial with respect to phi, and same for y, and then z is z, so no one's confused. Now we're gonna do the second derivative. We're gonna persevere. So I'm just gonna do x again, and we can extrapolate. We can use the product rule here, which again is another simple calculus rule that gets horribly confusing horribly fast in this circumstance. So, hello, Mr. Computer. No, it doesn't want to, does it? Can we be nice? Okay, we're gonna be nice. Right, great. So, what our second derivative is going to be is first derivative squared, or rather times itself, which is cos phi partial, that still looks like a 0. Nope. That'll do. Partial over partial r, minus sine phi over r partial over partial phi. And that's squared, in fact, which is going to result in cos phi, mental maths, there, bracket, cos phi, yeah, over r minus cos phi, that over partial r sine phi, over r partial phi. That will do. Which is equal to minus sine phi over r cos phi. That partial derivative with respect to r sine phi over r partial with respect to phi sine phi over r partial phi. Cool. Now we can expand all of our terms, and I'm not going to write that all out because it will get monotonous. But we see that when we add our terms, when we add the coefficient of the second partial derivative term, we get that cos squared phi plus sine squared phi, which is of course phi. Thank you, which is equal to 1. Useful. When we do the partial r, we get sine squared phi over r plus cos squared phi over r, which is equal to 1 over r, because we factor that out. And then finally, if we do the second derivative with respect to phi, we get sine squared phi over r plus cos phi over r equal to 1 over r squared. What do they say? Derivation of this is left as an exercise to the watcher. You can expand that if you want, or keep going with it. You just have to, expand each term and then sum them together, which is a bit of a pain. And so we see that all the other terms cancel perfectly if you mix the derivatives together. So if we, again, you could do this in more detail, I'm not going to. Laplacian squared in cylindrical coordinates is the partial r squared plus 1 over r from up there, partial r plus 1 over r squared, no, partial squared over partial phi squared, plus partial squared of z, or rather with respect to z, which is 1 over r partial phi. I wish there was a better way of writing this. I'm sure there is one, I just don't know it. That plus 1 over r squared, second derivative with respect to phi. Stop calling them partials, start calling them derivatives. I'm being silly. There we go. Second derivative with respect to z. And now finally, since we have an equation for the Laplacian and we have a time-independent form of the Schrödinger equation, we can start solving or deriving or whatever you want to call it for the cylindrical well. So we can define our potential inside the well as V, which takes in arguments. Arguments, do you call it that in physics? I don't know what the word is. I haven't done a physics degree. Inside the cylinder, r is less than some a, and z is between 0 and then some length and infinite outside of that. So that's our potential function. We can pop another line there if you want. And And now what we're going to do is substituting this into our earlier equation, our time-independent Schrödinger equation, h bar over 2 mu times 1 over r. This is the Laplacian from above. 1 over r times the derivative with respect to r times the derivative with respect to r plus 1 over r squared times the second derivative with respect to phi plus the second derivative with respect to z times the position, the spatial function of the wave equation. That was the weirdest E I've ever drawn. E times the same function. I'm not going to bother writing arguments because there's no need. Now, we propose a different separable solution here. Yeah. So, what we're going to say is we can split it into 1 over big R. Oh, wait, let me first define what I want to... Yeah, okay. So, if we take our spatial function in terms of R, phi, and Z to be some R, which takes little r, times a big phi. I'm going to draw my big phi like that, sure I will. Which takes little phi, and then Z, which takes little z. We can sub this into the above equation and divide everything by that so they cancel. And we get that 1 over r double dash, or I can do second derivative of r if you want, but I think r double dash should be fine since we know what r is, plus 1 over r prime not dash, plus 1 over r squared times our big one times the big one big phi. I'm gonna search up if this is phi. No. Maybe. Yeah, no, it is phi. Okay, I'm not crazy. Thank goodness. I've been calling it the wrong thing the whole video. I just have doubting myself. Now we're gonna add r and r z term here times z dash dash, and that's equal to, I don't have enough space. I made the board bigger and I still don't have enough space. 2 mu e over h bar squared, which is just minus k squared. And my voice is really messed up. Back to the physics. Stop distracting myself. We can isolate the z component. So 1 over, because it's easiest, 1 over z times z double prime is equal to minus k base z squared. What function could possibly fulfill this? I wonder. This equation, I don't know, you can work it out, but I do know actually, I lied. Z of z is equal to sine times that k of z. So it's just a sinusoidal function, which shouldn't be that surprising, considering it's a basic differential equation. Differential, not even. Yeah. No. You can find a sort of functional equation, sure. Anyway, we have boundary conditions here, the bane of all humankind, I guess. We know that we need to know that z of 0 equals to z of l, which is 0. So we can say that k base z is equal to p times pi over l for some integer p, for p in z. No, wait, there's a cool way of doing this. This is the black pen, red pen method. Look how cool that is. And so we can finally say that. Oh no, that's all we need to say. The next thing that I want to do, however, is take out the other parts. So r squared over big R times r double prime plus 1 over r prime. I hope this video isn't going on for too long. Plus r squared kr squared. And that's equal to 1 over, 1 over this times big phi double prime, which is m squared. M squared is a separation constant. And now we sort of get the angular equation for that big phi. We know that phi double prime plus m squared phi is equal to 0, and the equation that satisfies this is none other than, any guesses? Oh, I don't care. Phi of little phi is equal to e to the I am phi, not the International Maths Olympiad, but I am phi. M needs to be a integer, for m is an integer. Now the general solution involves the dreaded Bessel functions of the first and the second kinds. And what those are of r equals to a k base r plus b times y k base r of r. Bessel functiony stuff. We know the wave function must be physical, and we know that ym diverges when r is equal to 0. So if we set b equal to 0, we get that r of a. This is the cylindrical wall. R equals to a. That's equal to a to j k base r of a, and that's equal to 0 because that's the wall, you know. Now I think it's possible to learn these, but I'm not going to. The quantization condition, if we let this alpha mn be the nth 0 of the mth order Bessel function, this case it's j. The quantization condition here is that k base r of a is equal to this alpha, and hence k base r, better k base r is equal to alpha of m and n over a. And now we know that e is, well, we know that k squared equals to kr squared plus kz squared. We're really close. We can say that e of m, n, and p is equal to h bar squared k squared over 2 mu, which is h bar squared over 2 mu, got our original constants back, times k r squared plus kz squared. Finally, we can sub in our values of what we got above. H bar squared over 2 mu times alpha n over a squared plus p pi over l squared. L, M, and M, N, and P. L, M, N. Oh, I missed out O. Doesn't matter. That one looked a bit silly. So, we can, in fact, put a box around that because, well, actually, we'll write it out nice and beautifully at the end. E of M, N, P. These are the energy states. I'll explain a bit more of what this means in a moment, or rather what the significance of this is. 2 mu times alpha squared of mn, not mm, over a squared plus p squared pi squared over big L squared. And that is our final solution, and we can put a box around it. What does this mean? Well, we have the term here on the left that confines it is radial confinement, so it features two useful things. It features alpha of mn, which is the nth zero of the Bessel function, and it represents like the nodes of the wave function. And then below we've got a cool thing, which is actually the Heisenberg uncertainty principle manifesting in our equation here, where A is the radius of the cylinder. So as the radius decreases, the energy increases, which is like yeah, it's the Heisenberg uncertainty principle essentially. And then secondly, we have this longitudinal confinement, which is just the standard energy essentially. So P is the longitudinal quantum number, and L is the length of the cylinder. H bar is H bar. Mu is the particle mass. M is the azimuthal quantum number, and N is the radial quantum number. And those both arise from our two terms. So that's what it comes from, and this allows us to calculate the energy states inside of a cylindrical well. I hope that you enjoyed the video, and I will hopefully see you soon. Goodbye.